All right. So here we are at the last lecture of this module, talking about Newton's third law. We've already did laws 1 and 2. So with Newton's third law, we're actually going to zoom out a bit. We've talked about individual forces acting on, forces acting on a single object and talking about how it makes that object move. What we're going to talk about now is the fact that every force has an equal and opposite reaction. So if you have a force pointing this way, you're going to have a force pointing equal and opposite. Okay, it sounds a little nebulous right now, but we'll see what that means in just a second. So it's true that no push or pull ever occurs alone. So basically all these forces we've been talking about, they should have a counterpart somewhere. But the question is, where are they? We've not talked about those counterpart forces. We've just talked about those original forces. So every force, oops. Go. So every force is part of an equal and opposite, or every force is part of an interaction pair. And this is going to be between one thing and another thing. So an interaction requires a pair of forces acting on two separate objects. Okay, so we've been drawing forces on objects. So think of something like this. There's our interaction. Here's our interaction pair, these two objects with two forces pointed toward each other. So in an action-reaction pair, the question might arise, okay, well, if we're going to define one of these as an action, one as a reaction, which one is the action and which one is the reaction? Well, Isaac Newton would say, well, that it doesn't matter. It doesn't matter which one is doing the exerting and which one is receiving the other force, which one's the reaction. They're both supposed to be treated equally. So since they're essentially perfectly symmetrical, equal and opposite, it doesn't matter which one you call the action and which one you call the reaction force. They're always paired, and you can call one of them the action force or the other. The mathematics works out the same. So just an example of this is here on the right, we have a hammer, which exerts a force on a stake. Okay, so the hammer is up here. Okay, this hammer is going to start with some velocity that is not zero, right? It could come down at 100 meters per second, who knows? But this hammer is going to come down, and when it hits this stake, it's going to exert a force, right? So here's our force. It'll be hard to see. There we go. So here's our force. We also know that when this thing hits this stake, it's going to stop, right? It's going to have no velocity. So if it starts with velocity and then ends with no velocity, that's definitely a change in velocity. And we know that a change in velocity is caused by a force. Okay, so let's think about this. We have this hammer coming down and striking this stake. The hammer is exerting a force on the stake, but what force causes this? What force causes the velocity of the hammer to slow down to zero? Well, that has to be from, oops. That has to be from here. That has to be provided by the stake. So that's where the whole idea of the equal opposite reactions come from. You can kind of think about this as a bit of like a normal force. It's perpendicular to the surface. It's going to push back on the hammer. But this normal force is what's actually causing, is what's acting on the hammer to cause the hammer to decel. So that's why when you look at these interactions between two objects, you're going to see always two forces that are equal and opposite. Okay, so Newton's third law says that whenever one object exerts a force on the second object simultaneously exerts equal and opposite force on the first. And we saw that on the previous slide. We had the hammer exerting a force on the stake, then the stake exerting an equal and opposite force on the first. Remember, that's what caused the stake to stop, or the hammer to stop. So if one force is called the action force, and the other force is called the reaction force, we can actually simplify this statement of Newton's third law. Making this change, we can actually simply say for every action, there is always an equal and opposite reaction, just like we saw in the previous slide. So action and reaction refer to forces. It doesn't matter which one is called the action and which one is called the reaction. They both have to be there. You can call them, you can switch those names around as much as you want to. The mathematics will still work out. So here's just a couple of examples of these force action reaction pairs. We've already looked at the hammer and stake example. So the hammer hits the stake hits and stops the hammer. So that's coming back up. You can see that our action forces are solid vectors. Reaction forces are dotted vectors. Additionally, we have tires pushing the road backward. So the tire is going to spin this way. Okay. So that the road's not flying off into the sunset. The road's stationary. Okay. Which means as this tire turns, because the road's not moving anywhere, it's got to supply a reaction force. So the road's going to push the tires forward. And that's how we get our forward movement in a car. Same thing here with a jet. So we get the exhaust going backwards, and then the reaction would be all those exhaust gases sort of building up, and then they're sort of pushing off of each other, and that's what gives the jet its propulsion forward. And we can even look at just the most simple example, dropping a ball. So Earth pulls down on the ball, but the ball is also going to pull up ever so slightly, like immeasurably small, is going to have this little tug upward on the Earth. I mean, the Earth is so huge, you're not going to physically feel the Earth moving up toward a little ball. But that does happen. You can calculate it. It's a very, very, very small, like tiny little amount that the Earth would move up while the ball is dropping toward it. The point is, all of these interaction pairs, the force vectors are the same length. Okay. Force vectors are always the same length, but opposite direction. Okay, now you might ask the question, since all forces have an action and reaction component, and action and reaction forces are equal and opposite, how come everything ever just doesn't cancel out with its own action reaction pair, and then nothing in the universe would ever move? So the way to think about that would be how you define your system. So if we consider a couple different systems here, where an apple is pulling an orange in a cart by this taut rope. So this rope is going to have tension in it. Okay. So in this first case here, or in all the cases, the apple is going to pull. Okay. Now it's a little weird here, but the apple is pulling forward. Okay. So let's do red for the apple. So the apple's pulling forward. Okay, with the rope, but that's a tension force, right? And we know there's equal and opposite forces. So as the apple pulls forward, the inertia of the orange is going to be resisting, right? We got to have a taut rope with tension on each side. So this orange is going to be resisting. Okay. So the essentially the orange is going to be pulling back, or at least the inertia of this thing is going to be pulling back. Now we know that these two things, they are equal and opposite. And this is going to be the case for all of them. Okay. Even though there are two equal and opposite forces here in this first one, the system that we picked, we get to pick it. Okay. We can pick whatever we want to. So here we just picked this system, just the orange in the cart. The system only encompasses the orange, thus it is being pulled by an external force. Okay, so here is essentially all we're seeing is what's in the system, right? This is all we get to see. It's what's in the system. This becomes an external force because it is not inside our system that we defined ourselves. Okay, now all the acceleration stuff we've talked about, where the vector is pointing in a certain direction, that applies here to this vector, right? Right there. The action, we can actually use Newton's second law here. F equals ma, and we can do all of our fun Newton's second law of math. So the pair to this force, its friend that always shows up is outside of our system. Okay, so here we don't care about it, it's an external force. Okay, well, we could redefine our system to include both, right? All right. Well, so here we have two equal and opposite forces internal to the system. Okay, that's true. Those two equal and opposite forces are now inside our system that we've defined. And again, we can define a system however we want to. These cancel out now. Okay, they're equal and opposite. They're done. They've canceled out. But we know the cart's still moving. So how does the cart move if those two forces are canceling each other out inside the system? So the last thing we need to consider is if we have these two equal and opposite forces within the system canceling each other out, okay, we don't even care. Where does this forward force come from that's actually pulling the system forward? And for that, we have to consider another external interaction. So the apple's interaction with the ground, okay, that's where this external force comes from. That's going to move the cart, and you can see that right here. So even though everything in the system is canceling out to zero, there's still an interaction with an external object. So there's still an external force. External force. So the moral of the story here is that you need to be really careful about how you think about your systems so you can make sure you get all of your action interaction pairs. You can make sure you identify all of your external forces. This whole idea of being inside a system and all of the forces inside the system canceling out, and this should be true in every situation. So inside a system, it should be the case that all of your forces have equal and opposite components. If you find one that doesn't, then you're going to find an external force somewhere. And this is exactly why you cannot push your car from the inside. If you push on the steering wheel and then the steering wheel will just push back. The only way you can actually push your car and move it yourself is if you're outside on the ground pushing it. So the car plus you system has to have some interaction with an external object. So the external object would have to be the ground. If it's just you sitting in your car, that's your enclosed system. You can't push the car that way. Um, and of course, as strange as it may seem, a falling object does pull the earth upward um, with as much force as the earth pulls the object downward. So again, whatever force the earth is pulling down with, so that's going to be weight equals mg. Whatever weight is pointed down from the object in free fall, that weight is going to be the same being pulled on the earth. So whatever this is going to be the same force as what's being pulled up. So the question might be, why don't we feel the earth go up? Well, think about the masses. Remember how mass or inertia is sort of like the laziness of an object in is inertia. Okay, well, if we think about the mass of the boulder, that's pretty small. It doesn't have a lot of inertia, so it's going to fall fairly easily. If we think about the earth, well, the earth has a huge mass, right? It doesn't want to move. So it's just going to barely move when it's trying to compensate for this force from the boulder. And we can see this a little more intuitively if we think about cannons and cannonballs. So when a cannonball is fired from a cannon, there is an interaction between the two objects, the cannonball and the cannon itself. A pair of forces act on both the cannon and cannonball. So the force exerted on the cannonball is as great as the reaction force exerted on the cannon. Okay, so that's why the cannon will recoil. There's a force pointing in that direction, and it's the same amount of force that's pushing the cannonball forward. But the question is, why doesn't the cannon recoil with the same speed as the cannon? So if this cannon leaves just hauling, why doesn't the cannon itself just fly backwards too at the same rate? Okay, so here's our question. Okay, well, let's take a look at this picture. We know that these two, vectors are the same length. They're equal, they're opposite, Newton's third law. Now let's think about what's going on here. So since the mass of the ball is small, okay, so this is, right, this is tiny. Okay, if the mass is small, what does that mean about the acceleration? We know that, I don't want to do that. Oh no. Good grief. There we go. We know that acceleration is inversely proportional to mass, right? So if the mass is tiny, if one's tiny, that means acceleration has to be big. Right, so now we know that this is why the cannonball is flying out so fast. So this is, we can sum it up as small small mass, large acceleration. Well, now let's do the other side. And again, given the fact that acceleration is inversely proportional, not equal to, but inversely proportional, I'm going to try and erase this one more time. That's strange. Okay. Let's write it this way. Since we know this, we've talked about it in previous lectures. Well, the mass of the cannon, that's the whole cannon. This is large, okay? So if the mass of the cannon is huge, one thing's big, that means acceleration has to be small. And that's due to that inverse relationship. Okay? So that's why it comes down to the inertia. That's why even though they have the same forces acting on them, the ball's going to go further, less inertia. The cannon itself is not going to go as far because it's more inertia. But it's important to remember that the sum of the forces is the same for both. Now we can actually keep applying this to rockets, helicopters, and airplanes. So a common misconception is that a rocket is propelled by the impact of its exhaust on the surrounding atmosphere, but that's actually not true. So a rocket is actually propelled by the collisions within the exhaust itself. So if we look at this picture, down here, all these little molecules, they're bumping into each other while they're coming out, right? So what's happening is it's sort of making like a stepping stone for this rocket. All these particles are sort of getting jumbled up at the bottom. And this is totally a Newton's third law reaction. Same thing we can talk about with a helicopter. You'll notice that on a helicopter, the blades are sort of slanted. And because of that, as they spin, it sort of hits air molecules, then forces them downwards. And if you force an air molecule downwards and change its direction, well, that's an acceleration, right? Actually, I want to draw this. Okay, so if you have an air molecule coming in, it hits the blade. Okay, well, this is a change in direction. We know that a change in direction is an acceleration, even if it's going at the same speed. So we know this is an acceleration. And we know if an acceleration exists, a force has to cause it. Okay, so there is the action force, and then the reaction force would simply be, well, the blade would apply the action force, knocking the particle down, but then the particle would apply the reaction force, which is lift. So that's how you're going to get the helicopter to actually start taking off, right? So yeah, the reaction force, the air particles provide the lift. And just to keep things simple, I'll use capital L as the lift vector. And it is a vector, it's got a magnitude and a direction. Airplane wings are similarly shaped for the same reason. So when lift equals weight, so when the lift and the weight equal each other, there's obviously no forces acting, or there's no net force acting, right? Because they're canceling each other out. So when this happens, a helicopter will just hover, right? Because it's not moving up or down. The lift and the weight are canceling each other out. Okay. Last thing is just revisiting some things with vectors, and then we'll call it a day. So just as a pair of vectors at right angles, as you'll remember, we can actually add those up and combine into a resultant. You'll remember that if we have two vectors, maybe force y in the y direction, force x direction. Remember how in previous lectures we used that tip to tail method to add them up to get a resultant vector? So this would be fy plus fx. Well, we can actually go backwards. We can start with a resultant vector and then break it up into its components. Okay, so we can do that here. So we have this vector, vector v. Now it's not really got on a coordinate system yet. It looks like we have a y-axis, but not an x-axis. Okay, so let's set this in a coordinate system. And remember, we can set up a coordinate system however we want to, but we'll make it easy. We'll say that, oh, I don't know, red can be our x direction and green can be our y direction. Okay, so this is just the axes. We've not made any vector components yet. Okay, so we have our x and our y direction. Now we need to know just how far to draw. So it looks like here in the example, they're going to do the y direction first. Okay. So now just take in how much of the vector v goes up, right? We just want this piece. So now we can label our y component. And then, of course, for the x component, we want how far over is this vector in the x direction. Looks like about here. So this is our fx. Okay, so we started essentially, and here's a final picture of the components, the y and x. Yeah, I guess good practice would be to make sure you're using the same letter. We've been talking about forces, so I was just in the habit of using a force, but we could put a v here and a v here. Here we go. All right, so you'll see that we actually started with one vector over here on the left and actually broke this down and wound up with two vectors here. So vector one, vector two. And we could still talk about our original vector, or we could talk about just its y piece and just its x piece, depending on what we're talking about. The best way to see how breaking down a vector plays into Newton's second law, or sorry, Newton's third law, I think the best way to do that would just be to look at some examples. So here we have this monkey swinging from a rope, and it swings over and grabs the side of its cage. So maybe this is like at a zoo or something. Okay, so we know that it's not moving up or down, it's stationary. So the sum of the forces in the y direction, it's zero, no movement this way. It's not swinging back and forth, right? Because it's holding on to the side. So the sum of the forces in x direction, also zero. Now let's map out these vectors. Okay, well, it looks like we have, if this is our system right here, we'll just treat the monkey as a little dot here at the origin, right? This is x direction, this is y direction. Well, we have this tension. Okay, we have tension going up. Now we also have the weight of the monkey, because it does weigh something. Okay, that's going down. as always, toward the Earth. And we can even just call this W and not worry about mg, even though it's the same thing. Now, there's some more tension here, but here the book just labels it S, but it's where it's holding on to this wall or this cage or whatever. Okay. So that's here, S, we have the weight down, and then we have the tension from the rope. Okay, well, the cool thing is this S, this S vector, all of it is in the X direction. We don't have to break it down into its X and Y components. It's all already there. Okay, and then the weight, this is all in the Y direction. We don't have to break it down. It's all already in one of the directions. Now, the only other thing would be the tension. So this image over here on the right only does part of the breakdown. So let's ignore this because I think we can do better because it's sort of an incomplete picture. So let's break down, let's use orange. Okay, let's break down the tension here and we'll break it down into its X and Y components. And then we'll look at how Newton's law, a third law, plays into this. Okay, so in the Y direction, whoa, there we go. In the Y direction, we see that we have this much tension pointing straight up in the Y direction. And then we also see that we have this much tension in the X direction. Now, here's the thing. We know that there's got to be summed forces that equal 0 here. Okay, we know that this monkey's not moving up and down or side to side. So what's happening is these two vectors cancel each other out. We know that just the Y component, just the vertical piece of tension, cancels out all of the weight going down. And then we know that just the X component of the tension cancels all of that arm tension, okay? So what we had to do here is, obviously we had all the weight in one direction and this arm stretched out in the X direction. So we had to use pieces of a third vector to show where the canceling happened, okay? So these are equal opposite, but it's not the whole vector, it's not the whole tension vector itself, it's just a piece of the tension vector. Okay, now let's keep moving on. Here's one. This one might be a little more tricky, but it's a neat example. Okay, so here we have this ice cube, and I'm going to go ahead and I'm going to define our coordinate system like this. X direction is horizontal, Y direction is up and down. So we know that we have the normal force up and we have the weight down, which means nothing crazy is happening, so these two things are going to cancel each other out. This block is flying up or down. But now if we start to like turn it and start making an incline, look at what happens. So here's our coordinate system again. But now the normal force, remember, is always, oops, there we go, always 90 degrees to surface. The normal force will always turn with your surface, right? So whatever angle we start making our incline, that's how much our normal force is going to tilt over. But what's canceling out the normal force now? Like these aren't equal and opposite. They're not pointing in the opposite direction anymore. So the trick is, and this is where this one gets more complicated. The trick is the normal force is just canceling out, the normal force is canceled out by part of the weight. So you can see the weight is always going to point straight down toward Earth. As we make this incline steeper and steeper, mg always points straight down. The normal force, no matter what, is always going to be at 90 degrees to the surface. So 90 degrees like this surface here. So the trick is we have to realize that part of the weight here is actually what's going to cancel out with the normal force. We just need to figure out how much. So what we can do is connect this over to our y-axis and realize that, let's see, weight in the y direction. This green piece is canceling out the normal force, but look at what we have now. We also have a blue piece, because this is in the x direction. So this weight vector now has the y component of it canceling out the normal force, and now it actually has an x piece. That's what's causing this block to start sliding down the ramp. And you can see if we make this even steeper, the same thing's going to happen again. Okay, so drawing in our, sorry, this is getting a little tricky on this angled block to draw. But nonetheless, we can connect this over to the y-axis, and we see that here's the y component of the weight. And then notice how we have a much longer x component. That means we're getting way more force in the x direction, which makes sense because this block should slide down much faster. And then if we go over here to perfectly vertical, we have no normal force at all, because there's no force that the normal force has to counteract, right? If we go back to our original thought here, so this is actually now the y direction, because we've turned it so much, we've actually turned it a full 90 degrees. So what's happening is all of this is all now in the x direction. And since it's all in the x direction, there's nothing in the y direction to warrant having a normal force. That's why it's 0. Okay, so these are a little confusing. I don't think the book goes through these examples quite as in depth as I did here. So sorry if it was a little bit tedious, but this is super helpful, and sort of understanding how these relationships work will be very beneficial in the future. So thank you for your patience while we walked through some very tedious examples of breaking down vectors and looking at Newton's third law. But that covers everything for Newton's laws. And then after this, we'll move on to, I think, momentum is the next topic. So be prepared for that next time.